All right, so I started off as a geology major and got up to mineralogy, and I was trying to identify minerals. And the instructor of the mineralogy class, he mentioned that there are people with 30 years of experience who still misidentify minerals. You know, about the same time I was taking chemistry, and chemistry, it looked like they had lots of sophisticated instruments that the geologists didn't have, because, you know, you put in an instrument, you could figure out what the mineral is. You know, minerals usually would be just a pure substance. And so I thought, wow, you know, this chemistry seems more sophisticated in that sense, but that was wrong. You know, geology is very sophisticated. They just can't wheel a gigantic instrument out into the desert. And so if I just would have stuck it out in geology, it would have been perfectly fine too. I could have done more analytical stuff with instrumentation and whatever else. But nonetheless, I decided to change my major and transferred to UCLA. I got my bachelor's at UCLA and then went on to UCSB to get my PhD eventually. In fact, at UCSB, I worked with some geologists, biologists, you know, electrical engineers, mechanical engineers. I was part of the material science research group there. And so, you know, the biologists, they were looking at abalone shells. You know, what makes abalone shells so tough? You know, what's the structure? Can you make a synthetic material comparable to that? Spider webs, you know, spider webs have incredible tensile strength. And so lots of natural materials that have very unique properties, desirable properties. And so we want to try to make those rather than, you know, get those from nature. Okay, then I started teaching, but let's talk about the course here. If you guys have any questions, feel free to interrupt me any time. But let's take a look at this course information sheet first. We have the catalog course description. And when you look at the catalog course description, there are periodic groupings, transition metal complexes, chemical equilibrium, thermodynamics. It seems to be spread out over a number of topics, but really it isn't. It's heavily biased towards one topic, and that is equilibrium. We spend more than half the course talking about equilibrium and equilibrium calculations. And so what are equilibrium scenarios what are the equilibrium scenarios that we're going to encounter? And if you think back at Chem 1A, I think the easiest way to understand what an equilibrium type calculation is to go back to stoichiometry. You know, when you have a stoichiometry problem, you just assume 100% reaction. You know, the limiting reactant is going to be completely consumed. You'll be left with nothing, and then you can calculate the theoretical yield, correct? But in Chem 1B, we're going to encounter partial reactions. You've seen partial reactions before. For example, weak acids partially ionize or partially hydrolyze in water, right? And so something like acetic acid, does it completely break apart into ions? No. It partially breaks apart. Well, in Chem 1B, we don't want to say partial. We want, you know, well, what is the percentage? You know, what percent of the acetic acid molecules break apart? You know, is it a fixed percentage, or how do we deal with it? And so we're going to spend the bulk of our time in Chem 1B looking at these partial chemical reactions. They don't go to completion, you know, and how to do the stoichiometry on them. So equilibrium is just stoichiometry for partial chemical reactions. And if there's some kind of infographic, that would be huge, because equilibrium is the biggest chunk of Chem 1B. And then the other topics are smaller time commitments. And so this is just an overview of the topics covered in the course. Essentially, it's just part 2 of general chemistry. And so we'll be using volume 2 of Petrucci. The course objectives here, you just want a solid, you know, fundamental understanding, as well as good problem-solving ability. That's what we'll try to develop in this course. There's some student learning outcomes. Just 2 of these are shown here. You know, one is about writing or predicting chemical reactions. The other is about wearing goggles in the lab. This is yet another, the scientific method. This is a student learning outcome in all our classes, starting with Chem 4. You know, all students should, by the end of that course, understand what the scientific method is. At least be able to give an example of it. Prerequisite, Chem 1A. Required materials. Well, the 11th edition of Petrucci is already out, but we're going to continue with the 10th edition, just volume 2. Or if you have the whole book, you're set. The lab manual is a little different than the Chem 1A. The Chem 1A, I think, was a loose leaf. Right? This one is a bound lab manual. It's quite a bit more pricey. I think $28 because of that. That's in the bookstore. You'll need a lab notebook. Well, it's just a regular composition notebook, except not college ruled or wide ruled. I'd like it quad ruled, if you can. Some people asked me this morning, is like a college ruled okay or wide ruled? It's okay. It's nice to have quad ruled because it's easier to make graphs and tables. That's all. But if you have no problem making tables in a regular line notebook, then no worries about that. Your Chem 1A safety goggles should be okay. Okay, number 6, the scientific calculator. Here's where you might consider getting a different calculator. I think in Chem 1A and Chem 4, they recommend like your basic scientific calculator, like the $10 version. I think. And the problem with the base model scientific calculator is it doesn't have an equation solver on it. And so it takes a lot more time to do quadratics. And so if you get the next level up, so the base level is about $10, the next level up is like $17. If you buy the $17 version of the scientific calculator, most likely it contains a quadratic equation solver. When we do these stoichiometry problems with these partial reactions, we have to solve the quadratic equation quite frequently, and it becomes tedious to do it, And so it's much easier just to punch in A, B, and C and get X spit out. Okay? And so the calculator that I like, but you could use any, TI, whatever. But the calculator I've been using is Casio FX 115ES. The last time I bought this, I bought it at Target, and I think it was about $15. But one of my students said they just bought it at Walmart for $11, so it's pretty cheap. Or a comparable one. But what you're going to look for is one that's approved for the SAT. You can't have a programmable calculator. This is not a programmable. This is just a calculator, standard one, with the ability to do equations and solve equations. So just make sure it has the quadratic equation solver. This is optional. You don't have to. A lot of people last year, they didn't get this. They said they're plenty fast now solving the quadratic. They don't need to do it. So they didn't spend the money. But it doesn't hurt. If you only have one calculator, it's nice to have a backup calculator also. All right, or comparable. All right, item 7 is a fine point permanent marker like a Sharpie pen. We have Sharpie pens in the lab, but we just have a limited number. And so if you don't mind sharing, you don't have to get this. But if you want one for yourself, it saves time. Just buy one. They aren't that expensive. So the recommended materials, lab coat or apron. This is nice to have. And in fact, Santa Monica College has just started requiring these for everyone in the laboratory. UCLA has been doing this for a while because they had a number of accidents, and that was one of the safety recommendations, that everybody wears a lab coat in lab. And so I bought a lab coat a couple of years ago, and so I'm not sure if the price, maybe the price has actually gone down, but the lab coat I bought was $27, I think, off Amazon. A nice white lab coat. It wasn't cotton. The last cotton lab coat I bought was around $80 or $90 from a chemical supply house. And so you could get those online. And they're nice to have. And you might as well get used to wearing it because you're going to have to wear that wherever you transfer. Another thing you're going to have to get used to wearing are gloves. At Santa Monica, I'm not sure if they require them at Santa Monica, but for sure at UCLA they require you to wear gloves. Well, there are two types of gloves that are standard in the chem lab, nitrile and latex. When I started, I used latex gloves all the time at UCLA, but the problem with latex is they don't breathe very well. And so your hands get all sweaty and they're uncomfortable. Nitrile gloves breathe a lot better. And so when I switched to nitrile, I never went back to latex gloves. Not only that, nitrile gloves, even though they breathe better, they're more chemical resistant than latex gloves. And so they offer a higher degree of protection. And so definitely look for nitrile gloves. They sell them everywhere. Right, required assignments. You're required to attend both lecture and lab. Lecture, because I have more of UC philosophy, if you don't show up at lecture, it's not going to hurt your grade. Myself, I would never miss a lecture. I make it a point to go to every single lecture. But you don't have to worry about that impacting your grade. But the labs, you do have to worry about that impacting your grade. And so do not miss the lab. If you do miss the lab, make sure you make up the material, of course. And what are we going to have on lab meetings? We're going to have the experiment, so we'll have to figure out some way that you can make up the experiment so you don't lose those points. Or we might have an exam on the lab day. Now, if you know you're going to miss a lab and we have a test on that particular lab day, then you can take it before, or you can take it after. If you take it after, you're going to get a penalty, up to like 10%, depending on the circumstances. It could drop you a grade. But try not to miss the exams, otherwise it becomes a big headache. The exams are going to be worth about half your grade, the regular midterm exams and quizzes. And so this is based on 1,000 points. The exams and quizzes will total out to 500 points. The quizzes are going to be low point value, just 5 points each. The exams are going to be a little higher, 50 to 65 points. Mm-hmm.
So exams will always fall on lab days, not on lecture days.
Right. Exams will always fall on lab days. The exams will typically last for an hour to an hour and a half. And so we'll do both lab and the test. Normally we start off with lab and then we end early and then finish off with the test. If you finish the test early, then you're free to leave, usually. The exams, there are going to be a lot of them because the way I do the exams in Chem 1B is I test you on each chapter. So once we finish a chapter, then you'll just have an exam just on that chapter. And so I don't have multiple chapters on a test unless I'm just doing part of the chapter. The quizzes, those aren't regular. Those will be sprinkled throughout the semester. But the exams, if you look on the syllabus, this last handout, and you look for when is the first exam scheduled, and you'll only see the final exam. The final exam is going to be on the last day. The way the exams are scheduled depends on, where I'm at. Sometimes I fall behind the schedule. If I fall behind, then we'll move the date a little bit. And so the way it works is once I finish a chapter or topic, then we'll have the test a week after. And so this week we're doing chemical reactions. So next week you can expect the test on chemical reactions. And the test, let's say we finish on Wednesday or Thursday, we should finish on Wednesday. Chemical reactions, we'll have the test the following Thursday, September 8th. Chemical reactions. Chapter 15, it looks short. Well, that's on the lab day, so that's 3 hours. Plus, it overlaps. So we'll probably start chapter 15 maybe on September 1st and end it on September 7th. The test on chapter 15 will be the following week, like September 15th. So most of the time the exam will be on a Thursday. Once in a while it will be on Tuesday. Are there any questions on how the exam schedule works out? No? Yes. You'll also have to do paper homework. And the paper homework is going to be worth 10% roughly of your grade, 100 points, give or take. And the paper homework, when is that due? Okay, so if we have the chemical reactions this week, and next week on September 8th we have the test for chemical reactions, the paper homework for chemical reactions will be due on Thursday, on the day of the exam, at the beginning of class. Okay? If you didn't finish it for any reason, or you didn't turn it in, you still can recoup points. At the end of the semester, I'll collect all late homework. So just by the end of the semester, if you get it done by then, you'll get half credit for late homework. The way the homework works is this. You have the complete solutions guide, and so theoretically, you should be able to get 100%. You could get 100% on the homework just by copying the answer from the solutions guide into your homework notebook or homework pages. But a lot of people say, oh, never tell the students to copy it. But I have a little bit different philosophy regarding homework. And that's because of this. Sometimes, when I was a student, I would be spending a lot of time on one problem. Like, pretty soon, 1 hour, 2 hours, 3 hours, getting very frustrated because I couldn't figure out this particular problem. And then I realized, there's not enough time to waste hours on just one specific problem, right? And so I changed. As a student, I wouldn't spend more than 5, 10, 15 minutes on a particular problem. If I couldn't figure it out, I'd move on. I wouldn't look straight at the solutions guide. I'd just move on. And then I was, as a student, studying ways of studying. And so what typically happened is, even though you moved on, it's not that you gave up on the problem. Your brain is making these neural connections or whatever else. And thinking, in your subconscious about how to solve that problem. I mean, this has happened to me many times where I was taking a final exam at UCLA and there was a problem on the final. I couldn't figure it out. It stumped me. But that was okay because a lot of the final exams at UCLA are written they have a different philosophy. They're written so that no students finish it. Because if a student finishes it, it's too easy. They want to get a full spectrum of scores, and so if somebody finishes it, you don't know how much higher this, or somebody gets 100%, you don't know how much higher the score could have gone, right? And so there are too many problems, and some of the problems are just extremely difficult, which means that the average on a lot of tests that I took at UCLA was like 60% was the average. There was nobody in the 90s, and then they got this full spectrum, right? But the class was graded on a curve, so it didn't really matter. I have a little bit different philosophy. I expect everyone to be able to finish and then go back and look at their answers, double check their calculations, that type of stuff. But getting back to this, so this problem completely stumped me, and I couldn't figure it out. And then later on, after the test, I was at Ralph's, and standing in the checkout line, and then all of a sudden it popped in my mind. Oh, it was so easy to solve. I should have just done this, this, and this. I forgot about it, but for some reason my subconscious was still working on it, right? And so the way I think about this homework is, if you're getting stumped, spend some time, 5, 10, 15 minutes, come back to it. If it still doesn't click, don't waste too much time. Go ahead and copy the solution out of the solutions manual and write it, because at least that'll register in your mind. And once it registers in your mind, then your subconscious will integrate that with all your other knowledge that you have. Does that make sense? Okay. And so this is why I don't care if you copy the answer or not, and so theoretically you should be able to get 100%. Everybody should be able to get 100%, right? But normally what I find semester after semester is only about a couple of percent of the people get 100%, and then I see a full range of scores on the homework. And that has to do with time commitments and other stuff. Okay. All right, so you're going to have 10 chapters worth of homework plus the chemical reactions handout. Now, where's the chemical reactions handout? That's on our Piazza site, which I'll show you in a little bit. The labs, we're going to have reports that are going to be due for the labs. The reports are the same thing. Once we finish the experiment, the report will be 1 week after we finish. That's the typical due date. So you'll have a week to complete the report, except for a few of them. You know, for example, qualitative analysis is a lengthy report, so I give extra time for that. The synthesis, you'll have lots of time to do that one because we're going to make that one into a formal scientific report. Titration, another formal scientific report, so you'll have extra time for those. And so these ones you'll have extra time. But the others are pretty simple reports. You know, you probably can finish it on the day that you complete the experiment, but I'll give you a week, okay, to do that. The final exam is going to be worth 20% of your grade, so, you know, roughly 200 points, depending on what the total is at the end. The grade breakdown, 88 for an A, 78 for a B, 65 for a C. All right, you have to be careful. This policy regarding the lab portion of the course is the same as Chem 1A. You know, if you fail the lab, no matter how well you're doing in the lecture, you will fail the class. So fail lab, fail the class. Failing the lab could involve excessive absences as well, not just your point total. All right, a note on cheating here. You know, academic honesty is expected. Special needs, if you have any special needs, the Special Resource Center has lots of things like test-taking center, etc. You can take advantage of those. Also let me know if I can help you with anything. Changes, any changes will be posted typically on Piazza or during lecture. And so what is Piazza? Let's take a look. Is that here? I saw about half the classes already registered. Was it pretty straightforward? How many of you are trying to add? 2 of you? Okay, so you didn't get the email invitation to Piazza. But you don't need the email invitation to Piazza. It's simple to join the class. All you need is an access code. The access code is written on the sheet here. So the access code for my class is just Chem 1B, all lowercase. The changes section. And so let's go to Piazza. And then you just sign up. There's very few chem classes. I think last semester I was the only chem class at El Camino. So it's easy to find. And then I'll just put in my email address. And password. And this is it here. So I have today's handouts here as PDFs. I'm going to download those. Here are your homework assignments. So this is the chemical reactions homework here. You can take a look at. There are, I think, 20 problems in there. And then here's the chapter homework from the book. All right, this is what we're talking about this week, the chemical reactions. I have some PowerPoints here. You know, chemical properties, part 1, part 2, part 3. We're going to go through these this week. I have some lab handouts. This is one I pass out in Chem 1A. And some other. And then I'm going to post the recordings on YouTube here. And so you could look at the YouTube channel, Chemistry ECC. I might end up changing the name of that. But at the time, there was only one. ECC chemist on there. All right, any questions about this?
How soon after do you post your lecture?
I try to post them that night. Sometimes there's a delay in getting them uploaded. When I used to record them on my phone, it would take like 4 hours to upload one video. And so sometimes it took up to 4 or 5 days to get that uploaded. But with this, I think they'll upload pretty fast. Get there. The video quality might not be as good. All right, the lecture. I record the lectures just in case you miss something. It's easy to miss things. When I was a student at UCLA, I would always ask my instructors, "Can I record your lecture?" I had a little voice recorder, and when they let me record the lecture, that's great because then I knew I would never miss anything in lecture. If they didn't let me record the lecture, then normally I miss a whole bunch of stuff, like 20%, 30%, depending on how fast they talk. Then if they didn't let me record the lecture, what I tried to do is this, because I tried to write down as fast as I can. I don't know shorthand. A lot of people who know shorthand can get everything, but that's a really useful thing to know. And so I tried to write down as much as I could, and then I tried to leave a block of time right after class to fill in the blanks. So I might not have written everything. Let's say I wrote down 60%. Well, if I wrote down 60%, I still remembered the other 40%. And so right after class, I would sit down and fill in all the blanks, all the missing things from my memory. If I didn't have a block of time right after class, let's say I had another class right after that, then that was always difficult because, after that next class, your short-term memory goes way down. They say by 3 hours you've lost maybe 60% of it. And so I tried to do as much as I could right after class. But if they allowed me to record the lecture, then, so easy, right? I'd get everything. And so I tweaked the way I studied a lot during my stay at UCLA, trying to find what worked best for me. And so let me share with you what worked best for me. When I first started at UCLA, I was I like to study from the book type of person. The book is accurate. The book has all the information. Right? But I ran into some serious trouble because UCLA is on quarters, 10-week, plus 11th week is the finals. And during that quarter, they'll have a 1,000-page book. Right? And so I like to study from the book. It means I didn't really rely too heavily on my notes. I just relied heavily on reading the book and highlighting the book and annotating the book, right? But it was impossible. Reading 5 pages of Chem would take 30 minutes, 45 minutes. Reading this 1,000-page book in 10 weeks was an engineering class. It was exactly the same. I read 5 pages, look at the time, wow, I've already spent 30 minutes reading 5 pages, 995 more pages, right, to go. And so I quickly realized that I needed to change, and the way I changed was to take better notes. And in fact, at UCLA, this is common. They have a note-taking service where a professional note-taker would go in, take notes. You can buy them. In fact, I heard that the price has gone up quite a lot. There's somebody told me, this was last week, somebody told me one class, the lecture notes are going for $345. Wow, it's expensive. Even when I was there as a student, the notes were really expensive. You had to pay. It was, I think it was $90 for my organic chemistry class. But a lot of classes, they don't have professional note takers, especially the higher level classes, small class size. And so I would just take as accurate of notes as possible. And if I had a recording, then it made it that much easier. So you'll have the recording, you can do that. Too, anything you might have missed, you can make sure to fill in the blanks. Also, UCLA, it's a 10-week, 10-week quarter, then you have the finals. And so when do you start studying for the final exam? Well, I used to wait, the week, finals week, or the week before finals week, I'd start reviewing. But I quickly found that that caused a lot of stress for me. I just had so much stress during finals week. I figured I have to do something to lower my stress levels during finals week because it was unhealthy. And so the other thing I did was not only did I take really good notes, or as good as I could take, right? I would review them continuously. And so starting the first week, I would reread my notes. And so by the time the final exam came, I read my notes so many times that it was pretty much, I memorized it, everything, you know? And that's, my memory's bad. And so I would have to go over it again and again. And then finally it clicks. But you can start doing that right away. And so I do that like 2 or 3 times, 4 times a week. I would reread my notes. Rather than rereading the chapter. How long does it take to reread a chapter? A long time. All right. I'll talk more about this as we go along. So I have, how many people we're trying to add? 2 people? Let's see. I'll check tomorrow and see what the enrollment situation is. All right, we're going on to the scientific method. How many of you took Chem 1A over the summer? All right, that's good because then the material's pretty fresh in your mind, right? If you took it last year, how much of this have you forgotten? Probably lots. You know, I forget lots of stuff. And so a few months later, which brings me to an extreme scenario. When I was at UCLA, a friend of mine was preparing to take the MCAT. You know, this is the entrance exam test for medical school, the MCAT. The MCAT has a lot of chemistry in it. And so he's a biology major. He was a biology major at the time, and he asked me to help him review the chemistry. So I said, sure, I'll help you. And so we sat down and we started reviewing the chemistry. This is general chemistry. General chemistry is stuff he had like 4 years ago or 5 years ago. Probably it was 5 years ago at that time that he took general chem. And I realized that he forgot everything. He didn't remember anything. And so it was impossible. It was impossible to get him ready to take the MCAT, which was happening in like a couple of months, 3 months or something. 3 months there's no way he could relearn everything in 3 months. You know, it was just too much. He forgot. And yeah, that was the case because he ended up, after finishing at UCLA with his bio degree, he ended up taking 3 years off and reviewing everything. You know, all these classes, he completely forgot all the material. You know, once the final exam was done, that was it. He didn't want to think about that class ever again. Well, not until the MCAT came, right? And then he started to worry about it. And so, but he eventually got in there, so he worked hard at reviewing all that stuff, but I wasn't able to help him. And so it's nice to have a set of notes, because if you have a set of notes, let's say 3, 4, 5 years down the road, you decide to take the MCAT, what are you going to review? Well, are you going to start reviewing your notes right before the MCAT? That's probably not a good idea. You know, if you want to retain the stuff in your memory, right, it's probably better if you're thinking you're going to take the MCAT to review it on a regular cycle so that it stays permanently fixed in your memory. Well, this is just the same type of stuff, just on a shorter time scale. You know, for our final exam, when you want to start reviewing material, this week. And so the scientific method, this is one of our SLOs in Chem 4, which is Intro Chem, and Chem 1A. And so that's something everybody should know. So let's start with that, review of the scientific method. What exactly is the scientific method? You know, the steps of the scientific method, or what is the scientific method? You just take it, you know, if you've forgotten it, that's fine. Just take a guess at it. Uh-huh.
Like testing a hypothesis?
Testing a hypothesis? That's good. That's one I hear all the time. You know, you propose a hypothesis and then test it using experiments. In biology, that's usually the way it's presented. Right? How else? Anything else beyond testing a hypothesis? You want to come up with a question, right, or hypothesis, or something of that sort. What about in chemistry, like in Petrucci, Chem 1A? How did he present the scientific method? Did he say we propose a hypothesis and then test it? Is that what Petrucci, this is way back in chapter 1. Yeah?
The second test over the summer.
Well, I'm going to modify what Petrucci says a little bit. What we do, what scientists typically do is they just take observations. There doesn't have to be a question or a hypothesis. You just observe nature. When you observe nature enough, then you'll start to recognize certain patterns or trends in nature. And so from these observations, patterns or trends might emerge. So, for example, when people were doing chemical reactions in the, let's say, 1800s, one thing they noticed is the total mass of the reactants equals the total mass of product. And they always saw this, no matter what chemical reaction they did. Even burning a candle, the candle mass decreased, but the gases, CO2 and water vapor, compensated for that lost mass. And so that was a pattern, and this pattern occurred repeatedly. And if the pattern occurs repeatedly, then we might just call that a law. And so, for example, the law of conservation of mass or the law of conservation of matter, the mass of the reactants is equal to the mass of the products. Mass is conserved, neither created nor destroyed. That was the earlier. Other observations. What happens if you double the pressure of a gas? If you double the pressure of a gas, what happens to the volume? So we go from 1 atmosphere to 2 atmospheres. The volume decreases by how much? By half. Right? If we triple it, then it decreases by a third, etc. And so, those things, those types of observations, we can incorporate into a law. Typically, laws are the most concise, definition of this pattern or trend, and usually the most concise definition of a pattern or trend is a mathematical equation. And so laws, laws aren't always this, but laws are typically what we call empirical equations. Empirical equations, empirical is just based on observations. So these are equations that are based on observation. And based on the observations of a gas, for example, we could come up with the ideal gas law, PV equals nRT. That's an empirical equation. It's just a mathematical equation that fits the observations for the physical properties of a gas. Or, the mass of the reactants is equal to the mass of the product. Well, I need to put a little asterisk here because this needs to be modified a little bit. More sensitive mass determinations will show that some of the mass might be converted into energy, etc. All right, now we have this, but you think, okay, here I have a mathematical equation that fits. And what you can do with these empirical equations is you can make predictions. For example, if I quadruple the pressure, what's going to happen to the volume? If I increase the pressure by tenfold, what will happen to the volume? And so based on these empirical equations, we can make certain predictions. But, what is the origin of this particular equation? Where does it come from? And so that's where we come up with a hypothesis. And so what is the definition of a hypothesis? A hypothesis would be what we call a fundamental explanation or description. We just call it a fundamental description of the observations. And so where does this ideal gas law come from? That ideal gas law just comes from modeling how that gas behaves, taking measurements of volume versus pressure, or volume versus temperature, or pressure versus temperature, and then just trying to summarize that in the most concise definition possible. But does that tell us, fundamentally why the gas behaves this way? No. And so we hypothesize things, and the hypothesis for this might be that gases are made up of a lot of empty space and tiny particles. Right? And if it's made up that way, then we can come up with a theory, perhaps kinetic molecular theory, to explain the behavior of the gases, or to describe the behavior of the gases. And so what's the difference between a hypothesis and a theory? Well, they're both fundamental descriptions of the observations. The difference between a hypothesis and a theory is the hypothesis is what we call a tentative description, and a theory would be widely accepted. But even if we have something that's widely accepted, sometimes theories change or abandon. Can you think of a theory from Chem 1A that was abandoned or changed?
Phlogiston?
Oh, yeah. The theory of matter, right? Phlogiston, or whatever they call it. Yeah. That was abandoned. A better theory came up for that.
Bohr's atomic theory?
Bohr's atomic theory, yeah. Well, we'll come back to the phlogiston, but Bohr's atomic theory was one that was changed or abandoned. Because a theory has to do two things. One, it has to be a fundamental description of observations, and two, a theory has to predict new, unforeseen observations. New, unforeseen observations. So one thing that the Bohr theory could not do was predict, the spectrum of helium. It could predict the spectrum of hydrogen, but you go to the next most complicated atom, helium, and it failed. Where did the Bohr theory come from? Well, if we go back to the Bohr theory came from observation. Some strange lines were observed in the visible spectrum of the hydrogen atom. Those observations fit some type of pattern, and it turned out this pattern can be or could be described by a mathematical or empirical equation. Do you guys remember the equation that was used to describe the strange light patterns in the hydrogen atom? If you look at the light patterns in the hydrogen atom, a bunch of lines here in the line spectrum. Do you guys, is this ringing a bell? Then we had an empirical law that described this pattern. It was something like this: E is equal to minus R sub H, 1 over n final squared minus 1 over n initial squared. And so this is just a mathematical pattern that fit the placement of these lines. Just a mathematical equation. This equation, did it come from theory? No, this equation did not come from theory. This equation came from experimental facts, the observations of the experiment. And so therefore empirical. Empirical is just based on observations. Do you guys recall the name of this equation? R sub H. That guy, R sub H. First two letters of his name. Yeah. The Rydberg or Rydberg equation? Yeah. Well, the Rydberg equation, that's just an empirical equation. It doesn't come from theory, it just is a mathematical representation of those observations. And so, lots of people, not just Bohr, but lots of people hypothesize, what's happening? What's causing this pattern, right? That's where the hypothesis came in. And the hypothesis is that, what? Yeah, the hypothesis of things in atoms the electrons in the atoms can't have any energy, right? The electron, in other words, the electron energies aren't a continuum, but the electron energies are actually quantized. You know, there's certain values that they can have. They're forbidden values and allowed values. And then this led to the Bohr theory, but the problem with the Bohr theory is it could not predict new unforeseen observations. That one was helium, lithium, actually any other atom other than hydrogen. And so what replaced Bohr theory? Yeah, quantum mechanics, right? Quantum theory. Now, quantum theory was able to predict many things, many new unforeseen things, and one of them is a phenomenon called nuclear magnetic resonance. Nuclear magnetic resonance was predicted based on quantum theory. And based on that prediction, you know, new instruments were developed, like the MRI. The MRI came out of a prediction from quantum mechanics, you know, that atoms act as little bar magnets. Oh, we see lots of examples of this in Chem 1A. You know, this scientific method we see over and over again. So, for example, when we're talking about this, mass of the reactants is equal to mass of the products, that was a pattern that was observed over and over for many chemical reactions. So much so that they called it a law, right? We called it the law of conservation of mass. So what was the hypothesis for the law of conservation of mass? Well, there are competing hypotheses, right? One hypothesis was the phlogiston hypothesis. What was another hypothesis? What was competing against that? Phlogiston, whatever, you know, however you want to pronounce it. You know, why was mass being conserved, or matter? This is also called conservation of matter. You know, we can leave it at this. Then it's easy to predict, right? You start off with 10 grams, you're going to end up with 10 grams. We can use that over and over and make these predictions, and for the most part it's accurate, right? Unless you're looking at very, very minute quantities of mass, but for us it's accurate. But you know, is that it? Is that all? We're just going to leave it at that? Conservation of matter? No, you know, we want something more fundamental. We want a better description of what's happening. You know? And so what was that better description? Well, different people came up with different hypotheses. This is why it's tentative. So one hypothesis was phlogiston, but that was quickly abandoned because phlogiston couldn't, or there was a better hypothesis. What was the better hypothesis that explained atoms? Right. The better hypothesis was that matter consists of atoms. And initially that was tentative, you know, wasn't well accepted. But eventually, as the evidence kept piling on and on, it became widely accepted. And this wide acceptance is part of being a theory. And so atomic theory came out. And the initial atomic theory was Dalton's atomic theory. Okay, so atomic theory came about from the law of conservation of matter, which came about from the observations of chemical reactions. But what did it predict? Did atomic theory predict anything? Theory predicted plenty. One of the early successes of atomic theory, does anybody know one of the earliest predictions of atomic theory? This is way before we had all these sophisticated instruments, but one of the early successes of atomic theory was it predicted the... unfortunately, mass is more... I mean, it could predict mass in certain ways, you know, but mass was more complicated because Dalton initially said all atoms of an element have identical mass. Well, that's not true, you know, because we have isotopes, so... all atoms of an element do not have identical masses necessarily, unless there's just a single naturally occurring isotope, like phosphorus. All phosphorus atoms will have the same mass. This is only one isotope, phosphorus, etc. There are others that have single isotopes that are naturally abundant. One of the earliest predictions of Dalton's atomic theory was the law of multiple proportions. The law of multiple proportions, that is, atoms combine in simple whole number ratios to form molecules or compounds, came about from Dalton's atomic theory, whereas phlogiston could not. If you had phlogiston, then you could have any proportion. So let's say water could have, rather than being H2O, it could be H1.95830. And so you could have different quantities of hydrogen and continue on with that. And so that was it. But this we see over and over. So for example, where did Newton's laws of motion come from? Newton's laws of motion. Did Newton's laws of motion come from theory, or did Newton's laws of motion come from observations? Observations, right? The apple falling from the tree or whatever else. And so the Newton's law, you see pattern, trend, you get Newton's laws. And one of Newton's laws led to the theory of gravity. Right? And so this is the scientific method over and over again, and we should be able to see it. Now our approach in chemistry is, we approach this from different angles. Sometimes we just stop here at the law. So for example, PV equals nRT, and we just do PV equals nRT calculations. But when you think about that, anybody could do PV equals nRT calculations. You don't have to know anything about chemistry. So even an elementary school student who knows algebra, how to solve for one variable, can do it. Of course, we want to go beyond that and understand more. But chemists will rely on different approaches, and the different approaches are just raw observations versus a good understanding of theory. So if you know a lot of chemical facts, that is observations, and you have a good understanding of theory, then this is what I call the two-pronged approach to understanding chemistry. So here we're trying to understand PV equals nRT. Well, we can understand it from the raw observations, what happens to the gas volume, whatever else. Or we could try to understand it from the theory, kinetic molecular theory, whatnot. And the better the theoretical understanding, the less, I guess, memorization you have to do. But one thing I really hate to hear people say is that, memorization is worthless. You could just Google it or do something like that. And I think that is hurting a lot of students, not emphasizing the importance of knowing some basic factual knowledge. Because, you guys covered quantum mechanics, quantum theory in Chem 1A. Well, tell me what you can predict from quantum mechanics. If I wanted to know, okay, what color is SeO2? What color is SeO2? Well, I guess you could Google it, but what if Google doesn't have the color there? Well, then forget it. That's one thing. But if you wanted to know the color of SeO2, are you going to solve for that quantum mechanically? I guess you could, but wouldn't this be easier just to get some SeO2 and just look at what the color is? Yeah. And so chemists are going to know a lot of factual knowledge as well as some theoretical knowledge in order to understand chemistry. And so let's start off with an example of the scientific method. And so I'll go with carbon, and after carbon is nitrogen, oxygen, fluorine on the periodic table. And then below nitrogen is phosphorus, below oxygen, sulfur, and we have chlorine. Let's go with bromine and iodine here. All right, we're going to take some raw observations. And so this is what I want you to do. This is also a refresher. I want you to write down the formulas for the 8 anions. So for example, carbon would be carbonate, and that would be CO3 2 minus. And so just as a refresher, go ahead and write down, the formula for nitrate. Is there such thing as oxate? No. There's oxalate, but oxalate is C2O4. There's, is there such thing as fluorate? Yes, there is. Write down the formula. And so write down the formula for all these. You can work with your neighbor, or if you don't have a neighbor, you can work with the person behind you or in front of you if you want, or you could just work by yourself. But go ahead and do this. You know, for Chem 1B, somebody who has Chem 1A fresh in their memory, this should take like a minute, you know, a couple of minutes at the most. But it's easy to